Hello, class. As promised, today we're going to talk about how we analyze equilibrium points in two-dimensional systems of differential equations. So we looked at these systems in the last class, and we found the equilibria, and we could kind of get an idea of what was going on based on looking at kind of how the derivative was changing around it. But we're going to formalize that today and actually look at exactly what's going on at a particular equilibrium point. Okay, so just to kind of review where we were, so if you remember, if we had something like the system of differential equations dx dt equals y minus x squared, dy dt equals y minus x. When we looked at this, we found the null-clines, right, which were y equals x squared was the null-cline for dx dt. Dy dt, let me draw that a little bit better. And then for dy dt, the null-cline was y equals x. And so on the y minus x squared, that's where there's no horizontal motion, so this is strictly vertical. And we found that it was moving down in this section, up in this section, up in this section. And then similarly for the dy dt, the y null-cline, this is where there's only motion in the horizontal direction, there's no vertical. And so in this section it was increasing, and over here decreasing, and over here decreasing. Okay? And so from that, we looked at this and we talked a little bit about what happened at these equilibrium points. So remember, our equilibrium points are here at 1, 1, and here at 0, 0, which is where your x and your y null-clines cross. And at the 1, 1 null-cline, I talked a little bit about how you can see the arrows. If you follow kind of the arrows of motion, you get this kind of these hyperbolic paths that go away from the equilibrium point, right, and things like this. And so this is what's called a saddle. Okay, and the reason that this kind of happens is because if you look at where the motion is going, some of it is going out away from the equilibrium point, some of it is going in toward the equilibrium point. And so they kind of balance out and they veer into this kind of these paths that kind of skirt it but don't quite come close. Okay? The other point here, you can see the arrows. If you follow the arrows around 0, 0, though, you can see there's kind of this general curve. Okay? And so in a situation like this, it's a little bit harder to see what's going on because there's actually a lot of different things that can go on. It can spiral out and keep getting bigger and bigger as it follows these, or it could spiral in, so the opposite direction. It would spiral in and come closer and closer, or it can actually just kind of rotate around it. Okay? And so the way that we're going to analyze what actually happens at these equilibria is using something called the Jacobian. Okay, so the Jacobian matrix is the 2x2 matrix. In this case, since we're looking at systems of two variables, it'll be 2x2. If we looked at higher order systems, it would be more. You could do that in differential equations. We won't do it in this class. It's not quite as important for us. So it's the 2x2 matrix, which has all of the partial derivatives of these equations. Okay? So if you, let me explain what that means. So let's say this is f1, and this is, or let's say fx and fy. So this Jacobian matrix is going to be the matrix where you have dfx, dx, dfx, dy. All of my markers are dying. dfy, dx, and dfy, dy. Okay? So these are the derivatives of this. Now, if you haven't seen partial derivatives before, all this means is that you take the derivative of this function, but you take it with respect to x, and you treat everything else as a constant. Okay? So when we're taking the derivative with respect to x, y just acts as a constant. Okay? Similarly, if we're taking the derivative with respect to y, x just acts as a constant. Okay? And so in this particular case, so in this example, your Jacobian matrix would be the derivative of f sub x of the first equation with respect to x. So the derivative of y with respect to x is 0. It's a constant with respect to x, so that becomes 0. The derivative of x squared is 2x, and so we get minus 2x here. Okay? Derivative of f sub x with respect to y, derivative of y is 1. Derivative of x squared is 0 because x is a constant with respect to y. So we get 1. And then dfy sub x is negative 1. And dfy dy is positive 1. Okay? And so the Jacobian matrix for this system of differential equations is negative 2x, 1, negative 1, 1. Okay? So why are we interested in this? Well, what the Jacobian matrix tells us is kind of the linear behavior of our matrix. So if you remember back to Calc 1 when you were learning about derivatives, one of the ways of interpreting the derivative was it was the slope of the tangent line, right? So it told you basically if that curve were just a line at that point, if it were completely linear, this is how it would act. It would have this slope. And the Jacobian matrix tells us something similar for a two-dimensional system of equations. Now, a two-dimensional system of equations, of course, isn't going to act in a linear way, but it does have kind of linear behavior in certain directions, okay? And so those directions are related to the eigenvectors, and the behavior is related to the eigenvalues. So what we're going to do is we're going to take these Jacobian matrices and look at what the eigenvalues are when we're at the particular equilibrium. Okay? So you'll notice here that the Jacobian, now several of these are numbers, but that's just because this is a fairly simple system. I'll show you another one in a second. The Jacobian is a function of x and y. So you can plug in an x value, an x and y value. So for example, at our two equilibria points, so remember this had equilibria at 0, 0 was one of our equilibria, and 1, 1 was our other equilibria. At 0, 0, the Jacobian, because x is equal to 0, is going to be 0, 1, negative 1, 1. Okay? So that's kind of like the derivative of this system of equations at 0, 0. At 1, 1, it's going to be different. It's going to be negative 2, 1, negative 1, 1. And that makes a big difference in how the equation behaves. In the analogy to single dimension is if the slope is positive, it's increasing. If the slope is negative, it's decreasing. If the slope is 0, it's a constant, right? And so think about this as being a more complicated version of slope. And we're going to talk about exactly what these mean for the behavior of the system. Okay? Let me show you another example. Let's look at the predator-prey model and how we do the Jacobian of it, because that's actually similarly interesting. So if you look at your predator-prey model, so this is dx dt equals axy ax minus bxy dy dt equals cxy minus dy, right? That was our predator-prey model. X is our prey, y is our predator, right? And so these are the populations. And if we do the Jacobian, we take first the derivative of this with respect to x. So that's a minus, x is the variable. Everything else just acts as a constant. So a minus by is going to be our derivative with respect to x of this equation. If we take the derivative of this with respect to y, the first term gives us 0. The second term gives us negative bx. Okay? Because y is the only thing that acts as a variable. This is just a constant. Okay? So in the same way that the derivative of 2y would be 2, the derivative of bxy is bx, negative bx, since there's a negative sign there. Okay? Similarly, for dy dt, we're going to get the derivative with respect to x is cy, and then the derivative with respect to y is cx minus d. Okay? And so if you recall from the last lecture, and probably you don't exactly remember, but you'll remember we found two equilibria. So we had an equilibrium at 0, 0. And then the other equilibrium was at that point where our two null lines crossed. And that point was actually at d over c, comma a over b. Right? Because our two null lines were x equals d over c and y equals a over b. Right? So if you look back at your notes from that, you can see that. So at 0, 0, if we plug that in, we get the Jacobian matrix, y equals 0, so this becomes A. X equals 0, so since this only has one term, that's going to be 0, A, 0, 0, negative D. Okay? So we get A, 0, 0, negative D. And so that's going to tell us something about the behavior. Similarly, when we plug in D over C, A over B, plug that into our equation. So if we plug in y equals A over B, this becomes A minus B times A over B. A minus B times A over B. The B's cancel out, the A's cancel out. This becomes 0. If we plug in x equals D over C, we get negative BD over C. Down here, we get AC over B. And then down here, plugging in x equals D over C, again, we get 0. Okay? So at 0, 0, we have a Jacobian matrix that looks like this, A, 0, 0, negative D. At D over C, A over B, we have 0, negative BD over C, AC over B, 0 as our Jacobian matrix. And so in the next video, we'll talk about what that means for our behavior of our systems and see exactly what this looks like.